We're going to do some vertical motion examples. Vertical motion applies to any object that's thrown in the air and then is affected by only gravity after that point. So like a ball or any object that you just toss into the air will always have a parabolic path. It'll always look a little bit like a parabola. It goes up and then falls back down. So the formula for vertical motion is always negative g, where g stands for the constant of gravity, the acceleration of gravity, plus the initial velocity times time, and then plus the initial height. So the middle term here is velocity, like how fast or how hard it's thrown up into the air. The height is the original height from which it's thrown up into the air, and then the constant of gravity, or the coefficient here for t squared, is related to gravity based off of either meters or feet, depending on what unit of measurement you're using. It's 4.9 if it's meters, and you use a 16 there if it's measured in feet. But most of the time we'll be given most of that equation. So here's our first example. You can see it's measured in meters, which is why there's the negative 4.9. And then it's launched, so that's our velocity. That will go in the middle. And then from a height of 58.8 meters, which goes at the end. So it's always either 4.9 or 16 in front of the t squared, based off meters or feet, velocity in the middle, and height at the end. So what you're going to do from this point, in order to answer these questions, we're going to graph this. So on your graphing calculator, we're going to type in the formula negative 4.9 t squared. So I'm going to go to graph, and we'll type it in, negative 4.9. It said t squared, we're going to use x squared because that's what the calculator likes better. Plus our velocity was 19.6. And then plus the initial height, which was 58.8. So then you will get a parabola. Sometimes, depending on what your window settings are, it's going to look a little bit different. You can always scroll up or down. This one we can see is going, I have to scroll up a whole lot to get to the top of it. You can also change your window if you want to go into window settings and figure out what you would need those set to be. Here the question is only asking about when it strikes the ground. So when you graph it, the ground is represented by the x-axis. So let's keep scrolling down until we can see the x-axis here. There's our x-axis, so that's the ground. So we can see it hits the ground in the negative numbers, which doesn't really make sense since that's a time that we're looking at. And then it, again, over here, we can calculate exactly that value. Sometimes it's an integer, sometimes it's a strange decimal. And the intercepts are also called roots, so that's what we're selecting here. We want G-solve. We'll do most of our calculator. For most of the calculations will be done. And in this case, we want the roots, so F1. First, it gives us our negative root, which doesn't make sense for time. Then we get our positive root, which is 6. So the time that it strikes the ground again, when it comes back to the ground, would be 6 seconds. That's the root. It's when it hits the x-axis or the ground. Now we have another projectile launched upward at 64 feet per second. That's our velocity. From an 80-foot platform, that's the height. So 64 is the velocity. That goes in the middle. The height goes last. And then you just notice that these are measured in feet. So that means we're using 16 as opposed to 4.9. So it's negative 16 in the front. So we'll graph this equation in our calculator. Plus 64x plus 80 And now looking at the question, this time it's not asking when it hits the ground, it's asking when it reaches its maximum height. So that will be the top of the parabola, the vertex of the parabola. So if we scroll up, it's going to take a while. So instead I'm going to change my window. I'm just going to change this so we have a very large Y maximum. So it goes pretty high. So let's go to maybe 150. There we go. You can scroll up a little bit more and see it a little bit better. So that's the maximum height. So like I said, most of our calculations are done with G-solve. And we're looking for maximum height. So max, that makes sense. And it calculates it automatically, 144. So the object's maximum height is 144. Remember, this was in feet. And then the follow-up question, when will it attain this height? And that's just the x value, 2 seconds. So here we have another one. It talks about throwing your textbook off the roof. So you go to the roof of a 12-story building and look over the edge to a reflecting pool 160 feet below. So that 160 tells us that that is our height, which goes at the end. The other thing that's kind of hidden there is that it says feet, which means we have a negative 16 for feet instead of 4.9 for meters. And you drop your book over the edge at the same instant that Herman chucks his book straight down at 48 feet per second. How many seconds does his book beat yours into the water? So this is kind of a tough question. It's a two-part question. We have you that just drops it. And then we have Herman, who's standing right next to you. So the height's the same. But you just drop it, which means you have 0 velocity. Herman throws it down. So since he's throwing it down instead of up, we're actually going to, that velocity would be negative, and it's 48 feet per second. And it's looking for when it hits the water, or the ground in this case. Water specifically. kind of like the ground, so we're looking for the x-intercepts. So we can type in both of these at the exact same time. Negative 16 and then there's no velocity for u, and the height was 160. And then in y2, we can type in Herman, that threw his book down, so it's a negative velocity, 48, but it still started at that same 160 feet high. So you can see they both come down here, they both hit the ground. We're looking at the ground, so make sure you see your x-axis. And then we're going to calculate our roots, the zeros, so F1. The negative value is not what we're looking for. We are looking for the positive time value. Since we have them both typed in, it's asking which function we want. So let's do y1 first. I'll push execute for that. So we have our first negative value. We don't want that. We want the positive value. And then remember, this was us with no velocity. So it's about 3.16 seconds. And then we'll look at Herman. So we'll go back to gsolve. Again, we're looking at the root. And this time we need to change the function. So pick y2. We don't want the negative. We want the positive value for when it hits the ground. And that hits the ground at 2 seconds. So by how many seconds does his book beat yours into the water? Well, from 2 seconds to 3.1 seconds. That's a 1.16 seconds difference. So we have another one here. This one gives us the equation, so we don't need to come up with it. It's not even related to gravity. So it's a little bit different. The guy in accounting says, can be approximated by this formula. Find the daily production level that will minimize your cost. Anytime you have the word minimize or maximize, you're looking for the vertex. But if you didn't even know that, your calculator just has that function built into it. It's called the minimize. So we're going to type in this equation. You can delete both of these that we have going on. So this function we're typing in is 0.04x squared minus 8.504 plus 25,302. Two 5,302. Good. So this function isn't even visible at the moment. So you have two options. You can zoom out. You can until maybe you see it. Or if you just look at the values that are being used here, we have 25,000. So we need some really, really large numbers for our window here. So we could zoom out multiple times, or maybe we can just change our viewing window. 25,000, those were our y values. So we know we want to see the x-axis, which is 0. So anytime any negative number will be good there. We know that the maximum value that's mentioned there is 25,000 something. So we can type that in. Looks like maybe we're starting to see a little something though. We didn't change our x values because we're looking at the production. That's going to be probably a pretty large number also. So let's change this to a few hundred for sure, maybe even 1,000. See what we can see. So we're starting to see something right here. If you look back at our function real quick, we can see that this is a positive x squared, which means it's going to be an upward parabola. So since we're starting to see something and we know it's going up, we just scroll up a little bit. Start to see much more of this. And then the question is also asking about a minimum cost, which, like I mentioned, will be the bottom of the parabola. So G-solve is where all these calculations happen. And then right there, we've got minimum. And here we've got our two numbers. So if we look back at our problem, it says the cost for producing X thousands of units is this. So our cost is right there. That's like our Y in the function we typed in. So we want the minimum cost, which means we want the Y value, which is 24,850. And then that would be in dollars, which means it would make sense to keep the decimal points there. So, and 1 cent. So it's a little bit different than vertical motion. It's a different type of question, but it still goes through a graph, maybe changing your window to very large numbers if the function has large numbers in it.